So the second part of lecture is going to be about the normal curve. Here's a normal distribution meme joke, a normal distribution, a paranormal distribution. Okay, anyways, I'm probably the only one who finds that hilarious. But now we're actually talking about the bell shape. So Neil had a question at the end of part 1. Yes, just making sure I'm referencing the right person. Had a question about in part 1 about what the distribution or the sampling distribution is compared to a sampling distribution. Sample versus sampling. That's the major difference between those two terms. So a sample distribution hopefully looks something like this, right? And that's where we say, let's take a sample of 40 people. We gather their data. If we plotted it in a frequency distribution, hopefully it looks normal, right? But in this case, all of the raw scores of individuals would be the points that make up our frequencies. That's a sample distribution of a sample's values. In a sampling distribution, we should also have something that looks like this, which is a normal curve. But instead of individual people's scores making up the distribution, it would be a various number of sample means that make up the distribution. So a sampling distribution is the distribution or a set of sample means that have been collected from a population. So I think I have a note on distribution shape about the population not always being normal, but the sampling distribution of a population should always be normal. So generally, when we're talking about normal distribution, in a perfect world, we would have a symmetrical shape where we have the highest frequency in the center. And then as we branch out from that center point, which should be our mean in this case, right? As we branch out from that center point, we have a very equal frequency of occurrence of each value until we get to the end ranges of our distribution. In this perfectly symmetrical world, we would expect our mean, our median, and our mode, which are our 3 measures of central tendency, to be equal to each other. So they all assume the same value. To answer Neil's question, I just saw it. Should the shape of the sample distribution be normal as well? Yes, and I will address that in one slide. I love that you're on top of it though. Yes, so in this picture, the frequencies of our scores deviate from the mean in a predictable pattern. So they deviate the same amount as we move outwards towards the tails. But that's just what a normal curve is. Why do we want data to be normally distributed? Okay, so this is kind of answering Neil's question. The normal distribution of our sampling distribution from our population. So if we took a bunch of sample means, threw them in to a distribution, the shape should be normal. If you guys remember, we talked about, or I'm getting ahead of myself now. I'm so excited about talking about the normal curve. Why? Definitely should not be the highlight of my day. Okay. The normal distribution is an assumption for all parametric statistical tests. Okay. We assume that a population sampling distribution looks like a normal distribution, or that nice bell-shaped curve. You guys remember last week, and Juan actually asked a question at the beginning of class about external validity. Okay, so when we talk about external validity, we're referencing how generalizable are our results from our sample to the population. So is what we collected on our sample actually easy to translate to population terms? Okay, part of that generalizability is what we call statistical inference, and we'll talk about this more next week when we talk about hypotheses. Again, I hate the organization of this, but this is the best way I could come up with. But when we have statistical inference, that means is what happened in the sample what we would expect to happen in the population. So when we have a sampling distribution that we assume to be normally distributed, and more often than not it is, we also want our sample to have a normal distribution. Why? Because if the shapes of our distributions are the same, it's a lot easier to translate what happens in our sample onto what we would expect to happen in the population if we were actually able to collect everybody in the population. So hopefully that answered your question, Neil. So we would expect our sample to also be normally distributed because it better represents what we would expect to happen in the population, or at least the sampling distribution of the population. Okay. When we ask what measures are presented in the distribution, or later in some of your guys' activities and on the exam, you'll be asked to construct a distribution. And then we'll also assess the shape of the distribution. But when we construct it in a written format, we're going to be noting the mean and the standard deviation. That's why I presented measures of variability and central tendency before we talked about the normal curve, because it's important to know how those are calculated first. Okay. It's important to note that the mean and standard deviation are both values that can be influenced by extreme scores. Okay, because they take into account either we're adding all of the values in our data set or we're looking at the deviation of a value from the mean. So all of our scores are going to be included in the calculation for both mean and standard deviation. So that's something to keep in mind, especially when we start talking about distribution shape, which is our skewness and kurtosis. And it's also important to talk about when we start asking, like, how do we detect outliers? So these are the main ones, though, which no surprise, I already told you that. So that's why we want our data to be normally distributed. One, because if it's not normally distributed, we have extreme scores, then one, we're not going to be matching what our sampling distribution is. So the way that we transfer our sample results to our expected population results gets a little funky. And also it needs to be normally distributed so that the measures such as the mean and standard deviation that go into our statistical analyses are not going to affect the outcomes that we see. Normal distribution. It's an assumption for all of our parametric tests, similar to random sampling. Okay. As a side note, I also want to talk about the central limit theorem, which states that if a sample is large enough, a sampling distribution of a parameter will be normally distributed. Okay. So remember, a parameter is a measure of a population, some measure of population. Statistic is some measure of a sample. Okay. But the reason why we mention this, and that's why I use the term sampling distribution instead of saying the population is normally distributed. Okay, we have to say the sampling distribution, or the sample means thrown into a single distribution, because the actual population may not be normal. We don't actually know if it's normal or not because we never can collect the entire population. Or in rare cases, maybe you're able to calculate or collect the entire population, but very, very rarely do we actually have the whole shindig. Okay, so we don't actually know if the population is normal, but if you take a bunch of sample means, and this has been proven over and over and over again, which is why it's a theorem, right? And you have large enough samples, you plot all of those means in its own distribution, that sampling distribution should always be normal. If you have a large enough selection of sample means from your population. Okay. So I just literally said that. Okay, actual population may not be normal, but an accumulation of the means from randomly selected samples is expected to be normal. So that's our sampling distribution. Okay. In terms of what large enough means, this can vary based on what you're collecting. But generally speaking, we say that large samples, usually greater than about 30 subjects, should be large enough to give you your normal distribution. Things that are or samples that are smaller than that probably might be more subject to problems with distribution shape, but usually because of this central limit theorem, we say that if you have a sample that is 30 people or more, in most cases, you don't really need to do normality testing because they should automatically follow that sampling distribution normal curve. Okay. So again, central limit theorem, if you have a large enough sample, it should automatically assume a normal distribution to match the sampling distribution of a population. Questions? Chat. Yes. Do we primarily work with sample distributions or sampling distributions? We will work with sample distributions. But it's important to note that, important to understand that what we're comparing our sample distribution to is the sampling distribution, right? So in terms of is our sample significantly different than what we would expect from the population, or are two samples significantly different from each other, right? In order to compare those things, there needs to be some common ground, and the common ground is the normal distribution. So we'll be working with samples, but as you use your statistical inference and this is what I collected as my sample, this is what I think will happen in my population, that's the sampling distribution part comes in when you do the inference on what your results mean in the grand scheme of things. Oh. Okay. So let's talk about the normal curve some more. I kind of showed you guys a picture with a bunch of percentages in the last part one. That's what it's called. And those percentages actually mean something. And they're always going to be the same if you have a perfectly normal distribution. 0 is representing where the mean exists. And then we have +1, 2, and 3, and -1, 2, and 3 standard deviations from the mean. So these are standard deviation units, 1 standard deviation, 2 standard deviations, or 3 standard deviations. They're not standard deviations in the units of what we have measured, just making that clarification. Okay. But when we have a perfectly normal distribution, we can use this thing called the empirical rule to tell us how much of our data exists between standard deviations or within certain areas or regions under the curve. So if we wanted to look at the percentage of values that exist between -1 and +1, the empirical rule will state that if we added 34.13 and 34.13 together, we should get about 68%. So if we have a normal distribution, 68% of our people that we've collected in our sample should exist or have values between +1 and -1 standard deviations from the mean. You can kind of see where this is going. If we look at 95, right? The 95%, or if we added all of these percentages under the curve together between +2 and -2 standard deviations, we should have about 95% of our data existing in that region. And then we add on our extra about 4% to that, we end up with 99.7. So the empirical rule is also sometimes referred to as the 68, 95, 99.7 rule, which personally, way too many numbers to talk about. But the empirical rule is just stating that if we have a normally distributed or perfectly normal distribution, 68% of the data should be between 1 standard deviation from the mean, 95% should be between 2 standard deviations, and 99% should be between 3 standard deviations. Okay. Which then gets us talking about the area under the curve. So we can express the area under the curve, you can see here it's expressed as a percentage. We can also express it as a probability. So instead of a value from 0 to 100 as a percentage, we can also express it as a value from 0 to 1 as a probability. But it just tells us what the likelihood is of obtaining any given value or raw score within the distribution given certain pieces of information. So basically what I just described is a percentile, right? What percentage of values lie at or below a certain raw score of interest. So the things that we need to know are the mean, the standard deviation, and the sample size. Those hands down go into any calculation we're going to be dealing with in this area. And then we also need to know the raw score of interest, which I will typically give to you, okay? But when we're looking at a perfectly normal distribution, or we are assuming that our data have taken on a normal distribution, we can use certain calculations to figure out what's the probability that we have a value that exists, you know, at or below than this raw score, right? So in this case, I said my raw score is at -1 standard deviation. So whatever the raw score is at that point in my distribution, what's the probability that I have a value that is below that? Okay, or what's the area of the curve over here? And in some ways we can, if we're using the empirical rule and we know that we have a normal distribution, we can just add up these percentages down here. So 13.5, like about 15.6 or 7, right? So roughly 16% should lie down in this area. Okay, so you can add the percentages. We can also use something called z-scores, which I'll show you in a second, right? But we can get percentages below a certain value of interest. We can get percentages or probabilities above a certain value of interest, or we can also get them between. So I do examples of all of these for you guys today. There's also practice problems in the lecture, so you can always go back and look at them. But to find the probabilities, if we're using the empirical rule, we can either add the percentages in the bottom. More accurately, we can use z-scores, which are in terms of standard deviations. And this part always confuses people. Standard deviation tells us how far spread out our data is dispersed from the mean, right? And it's a plus or minus, so it's in increments. Z-scores are expressed in standard deviation units. You'll recall I said standard deviation when you calculate it using your sum of squares or square root of the sum of squares divided by sample size, right? That will tell you what the standard deviation is in the units of measurement. The standard deviation you get then goes into constructing your distribution. And we can either put our units in terms of our measured variable, or we can say +1, -1, +2, -2, +3, or -3 standard deviations. That is a standard deviation unit, 1, 2, or 3. We have 6 options, positive or negative, okay? Those standard deviation units are associated with z-scores. So if I said I have a value that's 1.5 standard deviations above the mean, that's the same as saying I'm at a z-score of 1.5. So they're synonymous with each other. Okay. When we calculate it, for a population versus a sample, it's the same calculation, so there's no degrees of freedom to consider. But what changes is the symbol. So we're primarily going to be working with the sample z-score. So basically, this is going to be the raw score of interest minus the mean of the sample divided by the standard deviation of the sample. Okay. And this is going to determine the probability that a value lies less than or equal to, and I use this term loosely because it's not always going to be less than or equal to, but we're looking at the probability that a value lies to the left, area to the left of a given z-score. You can tell left is important. Because if we're looking at, I'll just go back for a second because so you don't think I'm just yelling at you for no reason. If I wanted to know the probability in this region, I look up a z-score. That's gonna z-score roughly 2.5, let's say. That z-score gives me the probability under the curve to the left of that score. If I want to know the probability over here, I need to know that I have to take 100% minus the probability that lays in this region to get this region. Okay. Or if I'm doing a between situation, I need to know, right, the area to the left. That's important. So don't you forget it. That was a SpongeBob reference if you didn't know. You're probably laughing at me. That's fine. Okay. Anyways, before I get too carried away, I use less than or equal to very loosely. Usually your distribution is going to be made of values that are kind of on the worst end or like less desirable. On like the lower end of the mean, more desirable or better scores are going to be on the higher end of the mean. A perfect example is race times, right? The faster you run a race, the lower your time is. But the lower your time is, the better you actually did in the race. So a race would have very smaller numbers, right, on one end or on the upper end of the distribution with higher numbers at the lower end. But if you're doing like a test score, right, a greater number is actually more desirable than a smaller number most of the time. I don't know personal preferences, but that's why I say less than or equal to very loosely. Usually I like to say at or worse than a particular score of interest, just because that allows a little bit more flexibility with the variables you might be working with. But the important thing is the z-score gives you the probability to the left of your raw score of interest, which is x. Okay, this is another type of standard score. So we already talked about one type of standard score that was coefficient of variation, right? Where we're kind of taking any unit possible and we standardize it as a z-score. So then any and every variable can be compared to a z-score. So that's what we call it, a standard score. Okay. Now let's talk about the magical z table. I didn't make this meme, someone else made it, and I loved it, so I included it in the PowerPoint. But the z-score table gives us our probabilities. Yay! So all we need to know is how to read it, right? There's going to be a positive and a negative one. Positive is going to be for positive z-scores, negative for the negative z-scores. Yay, simple. We like it, okay? But again, and there's a picture in the table to remind you that you're getting the area to the left of where your z-score is in the table. When we read this, we calculate a z-score, we calculate it up to 2 decimal places. In order to read it, this first column here, you see 0, 0.0, 0, 0.1, 0.2, 0.3, goes all the way down to 3.4 because we usually aren't going to get anywhere past 3 standard deviations, right? But you find the first 2 values of your z-score. So let's say we had a z-score of 1.5 or 1.15, okay? We would say, okay, 1.1 is here. And then the 100th decimal place, you follow the columns on the top. So 0.05 or 1.15 would take us to this value, which admittedly is too small to read, but that would be the probability associated with the z-score. I actually have the table to pull up later so you can see it in bigger terms, but that's how you read it. Okay, so you calculate your z-score using your raw score minus your mean, divide by your standard deviation. You use that z-score value, find it on your table, depending if you have positive or negative value, and then the value that's in the grid is your probability of obtaining that value in your distribution. Okay, now, 2 important things. Again, we highlight. Z-table gives you the area to the left. Every time I ask people questions on this on the exam, there's always like a handful that get it wrong. I'm like, I say it so many times. Okay, which is also why my arrows are pointing to the left here, just in case you need a visual representation. But in the perspective, again, of standard deviations, you can see -1 standard deviation is equal to -1 z-scores, and so on and so forth for the rest of the values here. Again, the mean is in the center. Okay, so this particular example was looking at VO2. So when you build your distribution, we can either say 0, 1, 2, 3, and -1, or -2, -3. Or if you're looking at it in terms of the standard deviation with the units of measurement, in this case, it's 5. And the reason I know that is the distance between the mean and first standard deviation is 5 units. Okay, so if you're using the units of measurement, you just add your standard deviation upwards and you subtract it if you're going down, your distribution. But also, the other thing I wanted to point out is the percentiles that your z-scores are loosely associated with, right? So if we have a perfectly normal distribution, our 0 z-score mean should be roughly around the 50th percentile. So you'll notice that the positive z-table gives you values from 50 to 100, or close to 100. And the negative z-table will give you 50 all the way down to 0, which should make sense because we have 50% of the pop, or 50% of our data in one end and 50% in the other. Okay, this is if we have a perfect distribution though. So that's the other thing I put in red, is that z-scores give us estimated percentiles. We'll talk about exact percentiles next week, but it's important to remember you are assuming you have a perfectly normal distribution if you're using z-scores to calculate percentiles. So we call them estimated percentiles for that reason. Okay, do I have any questions? All right. Calculating z-scores, again, I've linked videos in your guys' PowerPoint, so you just right-click, open the hyperlink. But this is a practice for you guys. Basically, I've given you a raw score of interest, your sample mean, which is X bar, and your sample standard deviation. And all you're doing is you're going to take the raw score minus the mean, divide by the standard deviation. That gives you your z-score. You look that z-score up on the table, and then the table gives you your estimated percentile, which you can either present as a percentage or as a decimal between 0 and 1. This is not in the PowerPoint. It's actually in a practice, your practice problems PowerPoint. Okay. Well, there are solutions attached to that. This should be the next slide you guys have. Can someone confirm? Thumbs up or yes. Okay, cool. So this is this is an important one, constructing the distribution. This is what you actually get tested on, or there will hands down be a question on the exam on this. I guarantee it. So when you're constructing a distribution, you draw a normal distribution. Okay. You note where the mean is. You notate your standard deviations. Either it can be in your units of measurement or in standard deviation units. So basically options row 1 or 2. And then you locate where your raw score exists, shade the appropriate region. That's all I'm asking for when you construct a distribution. So I actually think we're going to run out of time to do these today, but I'll do one just so you see the process. I actually go through each one of these in the recorded lecture, only I don't use a z-table. So we'll do one example and then we'll get to the rest of the stuff. But if you want to skip in the pre-recorded video and go to this section, you'll see I actually draw everything out. Okay. So this is how I would phrase a question in your exams or quizzes or whatever. It's like, what's the probability that a person can curl at most 10 pounds, right? And then I give you the mean and standard deviation. I'm going to actually share my iPad now. If it works, please work. Oh, damn, that sucks. Okay, just kidding. New share. I'll draw. It's fine. I'm not happy about it, but it's fine. Okay, so first step. Oh, look, here we go. Woo! We draw a normal distribution. Okay, then we mark where our mean is. And then we mark where our standard deviations are. Again, you only have 3. My preference is listing 1, 2, and 3. -1, -2, and -3. You guys are probably like, what are you talking about? That looks fine. I'm a perfectionist, so it looks horrible, but it's okay. I'm crying. So these are standard deviation units. Let's say instead of standard deviation units, we wanted to note these as our actual pounds, our units of measurement. Our mean is 21. So we could put 21 there. And then to get our standard deviations past 21, if we're going above the mean, we just add. So you could handy dandy calculator on your phone, right? You say 21 plus the standard deviation 6.46. That gives us 27.46. Oh, no, 27.46. And then add 6.46 to that. We end up with, oh God, 33.92. That goes to 2 standard deviations, just so you're aware. Plus 6.46 gives us 40.38. If we were going below the mean, we start at 21 and subtract 6.46, which gives us 14.54. Subtract 6.46, subtract 6.46. Okay, so this would be in the units of measurement. So this is our pounds. And then our red numbers are our standard deviation units. Personally, I like the standard deviation units better, but it's totally up to you what you choose to use. So then we need to locate 10 pounds in our distribution. So that's where we're locating, right, our position of the raw score. If you have your raw units, generally speaking, 10 pounds should be between -1 and -2, because this is 14 minus 6. That should put us below 10. So you could use it, the raw score, find the raw score, estimate where that is based on the units of measurement if you constructed your distribution that way. The other way is to calculate the z-score. So z is going to be equal to our raw score of interest, which is 10, minus the mean, which is 21, divided by 6.46. So 10 minus 21 is -11, divided by 6.46 is -1.70. Okay. Rounding is important. So if you have a value that comes after this that is above 5, round up. Okay. But then, let me stop sharing for a second. And I want to now share my Z. This is why I wanted to do it on my iPad. It's a lot easier. So I have my Z table. And I have a negative Z-score. So I would go to my negative Z table. And in this first column over here, I look up negative 1.7. Luckily, it's a 0 after that, right? So negative 1.0 gives me a z-score, or not a z-score, a probability of 0 or 0.0446. You could also write this as 4.46%. Okay, so when I look at this on my graph, negative 1.7 should exist, let's say about here. My probability that my z-score gives me is the area to the left of that raw score of interest. So this is actually representative of 10 pounds as well as the z-score. Okay. And the probability that exists in here, let's call it P for now, is 4.46% or 0.446. So that is the answer to this question. If we wanted to find the probability that a value exists above a certain value, because we get the area to the left with z-scores, we just do 100 minus the probability that we calculate, and that 100 minus would give us this area over here. Okay, so if we wanted that probability, we do 100 minus. If we want, oh, no, thank you. I forgot to share. Let me go back. Guys, Zoom teaching, it's a different ballpark. Now you can see what I'm talking about. So this magenta line is representing where our raw score existed, right? It also represents what our z-score is that's associated with this raw score. And my z-table gave me a probability to the left of that raw score of interest, or the area to the left of my curve here. Okay, the area is 4.46% or 0.0446 if you're probability versus percentage. Either one is an acceptable answer. But what I was saying with this blue area here, if we wanted the probability that a value existed above a certain raw score of interest, so maybe I want to know if like what's the probability a person can curl at least 10 pounds, right? So in that case, 10 is still my raw score of interest, but I want to know the area above 10. Z-scores is going to give me this magenta area. So in order to find this blue area, I just have to do 1 minus the probability or 100 minus the percentage. Okay. So again, in the pre-recorded video, I do go over these examples, and I apologize because now we're going over time. But yeah, I would recommend watching those videos though. Also have practice problems in your practice problems PowerPoint. Those also have it's different, a different example with different variable. And on each slide after, I give you generally what the distribution would have looked like if you had both standard deviation units as well as units of the measurement that you collected. And then in the notes section is all of the actual calculations. So if I drag, this is what would happen in the notes. Okay. Okay. So very, very quickly, also wanted to talk about shape. If you have to leave, that's fine. I'm going to keep recording anyway, so you won't miss out on anything. But z-score summary, we can use them. You are welcome. We can use them to calculate estimated percentiles. We can also use them to create confidence intervals, which we'll do next week. And the other important thing is we can use them to calculate skewness and kurtosis. So skewness, both skewness and kurtosis are looking at outliers, which usually we see in the tails of the distribution, or the very tips. So if you hear me say like tail activity, we're referring to outliers or skewness or kurtosis. So Skewness is just looking at the symmetry of our distribution. So this red area here is no skewness, where we have perfect symmetry, same frequencies on each side. When we have positive skewness, that's this blue one here, that's where the tail is going to extend above the mean, okay? So it's also referred to as a right tail. But when this happens, that means we have an extreme score, right? Or one score that has a very, very low frequency, which is why our tail is extending out, right? And that is going to cause a shift in our measures of central tendency. So on a perfect distribution, our mean, our median, and our mode are all equal to each other. When we have an extreme score to the right, our mean gets dragged to the right. So mode and the median should relatively exist close to this peak. The extreme score and positive skewness would pull the mean somewhere over here. Okay, so in other words, the mean now becomes greater than the median and the mode, which is what this says right here. In negative skewness, it's just the opposite. So instead of the extreme score lying to the right of the mean, we have an extreme score lying to the left of the mean. So it's characterized by a left tail with an extreme score that is less than the mean, therefore dragging the mean towards the tail. So then we have a mean that is less than where our other central tendency measures should be located. Okay, so skewness is just a nice way to help us figure out if we have an outlier on one end or both ends of our distribution. Okay, usually if you're going to have an outlier, it's going to be on one side. But we don't discredit having outliers on both sides, which could potentially just not be a good thing altogether. So that's skewness, looking at symmetry and outliers on one side of the mean. Kurtosis is going to look at the number or the quantity of outliers that exist. So we also have positive and negative kurtosis. And usually people like to focus on the peak, but again, you want to focus on the tails because the tails are where the outliers exist. Positive kurtosis is going to usually have a very tall peak. So that's this blue arrow, this one here. It usually has a tall peak and very heavy tails. So if you want to think about it as a lot of your data is clustered into the center, and then there are very few or small frequencies of outliers that dot out to the end of the tails. Okay, so positive kurtosis means that you have a lot of outliers. Negative kurtosis is the opposite, where you have a flatter peak, and then your tails are lifting off of the distribution or off of the x-axis, right? So in other words, the frequency of your values at the ends of your distribution, either above or below the mean, are relatively similar to the frequencies that you see in the center. So that can be translated as that you have few to no outliers. Now that's the shape. The way that we evaluate the shape can be in various forms. So one way we can do this is by looking at the z-score of skewness and kurtosis, which we do actual calculation examples in the activity. So I re-explain all of this there as well. But we take the sample skewness, or what the skewness of our sample distribution looks like. We divide it by a standard error factor. It's different for both skewness and kurtosis. And then that gives us a z-score of skewness or kurtosis, which more or less tells us how similar our sample distribution or the shape of our sample distribution is to our population sampling distribution. Okay, so if we have a z-skew or z-kurt score that lies outside of 1.96, we say we have positive or negative skewness or kurtosis. If it's within 1.96, either above or below the mean, then we say we have relatively a normal distribution. Okay. So that's what this part explains. 1.96 or the significance of 1.96 will be explained next week. So we'll get there. So that's one way. So calculate skewness and kurtosis, or z-skew, z-kurt, to evaluate distribution shape. We can also assess normality or distribution shape by using these two tests in SPSS. So the Shapiro-Wilk test is the one that we're going to use, but there's also the Kolmogorov-Smirnov test. It just makes me think of vodka for some reason. I don't know why that's significant, but both of them have a null hypothesis that the distribution of the sample is not significantly different from a normal distribution of the population, assuming the population or the sampling distribution of the population is normal. We'll talk about p-values more next week, but just as a brief introduction, usually when your p-value is greater than 0.05, we accept the null hypothesis, meaning that we would argue the sample is normally distributed. When you have a p-value less than 0.05, we tend to reject the null, which would be the opposite of the statement that the sample is not normally distributed. Okay. In order to figure out why or what's causing, if we don't have a normally distributed sample, in order to figure out what's causing that, we can either look at our z-skew and z-kurt values to figure out if we have positive or negative skewness or kurtosis, or we could also test for outliers. And there's a variety of methods that can be used here, which I discussed in the activity as well. So the IQR method uses the interquartile range and basically says that at Q1, 1.5 times the interquartile range down from that Q1 value should kind of represent a boundary, with anything that's below that value would be considered an outlier. The same would go above 1.5 times the interquartile range above Q3 are values that would be considered outliers above the mean. It doesn't work on all outliers, but it is a general method that is frequently used, and it relatively is accurate. We can also use plots. So Excel has a box and whisker plot, and it'll put dots where outliers exist. You can also use a histogram, just looking at the general shape of a curve, right? If it's flat, if it has a tall peak, very slow frequencies on the outside, and you can change the dimensions or the bin width or the number of bins that are in the histogram to kind of sort out what your distribution generally looks like. You can also use percentages of z-scores, which we don't use in this class, but that is another method for testing outliers that looks at frequencies of values in various ranges of the distribution, kind of similar to the IQR method, but you're looking at the percentage of z-scores in terms of percentiles. So I don't know. I think that way is a little bit more complicated, so we don't talk about it. But as a final note to normality, so that we can get out of here, because I'm so sorry for keeping you guys. But normality doesn't need to be investigated for every parametric data set, right? Remember that the central limit theorem tells us that if we have a sample that's large enough, we should be able to relatively assume that we have a normal distribution. I like you guys to run normality tests in the beginning anyways, just so you understand that it is an important step to take, especially if you have a sample smaller than 30 people. But the different ways that we can check normality, particularly in small samples, would either be significance testing using the the Shapiro-Wilk tests. You could also use the plots to assess normality, and you can use the z-scores for skewness and kurtosis. So if I ask you, what is the distribution shape? You can use any three of these to pull out like what the distribution shape would look like. You can say, oh, I made a histogram and it looks like it's positively skewed. Or you can do significance testing and say that the data is not normally distributed because I got a p-value less than 0.05. Usually, if you did the Shapiro-Wilk test, I would ask for a follow-up, like, oh, well, do you have positive skewness, negative skewness, or positive kurtosis or negative kurtosis? And usually you would get that information from z-skew and z-kurt calculations. Okay, are there any questions before we leave? That was a lot. I apologize. Okay. Let it sit, digest it. Don't look at anything stats that's related to this topic for the rest of today. Come back, review it tomorrow or in days to come, and then let me know if you have questions, because I'm sure something will pop up. Remember that activity 1, discussion 1, and what is the other thing? Quiz 1, as well as all of your Start Here module stuff is due tonight. So make sure you get that in. I should be by my computer to check if there are any like last minute questions on the activity. I might not answer like later into the evening just because I sleep. What else? I think that's about it. Oh, you have data collection this week, so make sure you complete that. Aim for like Thursday midnight, but I have an issue with time zones, so I will lock the spreadsheet to editing on Friday morning. So just keep that in mind. You guys are free to go if you want to. I did see a question, so I'll keep the recording going. But have a great rest of your day/week. To answer Juan's question, explain the difference between sampling and sample distribution. So a sample distribution is taking all of the individual scores in our sample and plotting them in a frequency distribution. A sampling distribution we say sampling distribution of a population is where we would take a bunch of sample means and then we would plop them into a frequency distribution. So sampling distribution is a distribution of sample means. A sample distribution is a distribution of individual raw scores of a sample. Enrique, go ahead.
So it's like a whole dough, and then you make little pieces of cookies out of it. So each cookie is like a sample.
Yep.
And if you mix it up and then you take it's like a sampling.
Yeah. Exactly. And then Enrique had a question, are tests during class time? No. I think I write that, it's in the syllabus. But usually I give you from 8 a.m. to 11:59 p.m. to take any 3-hour window that you have to dedicate towards the exam. The tests they shouldn't take you the full 3 hours, but I give that because like online, sometimes test anxiety goes up. So, but yeah, as long as you have like a 2 to 3 hour window on Mondays that you can devote to taking the test, that's when they'll be open. The only exception is the final, because we have a set final time. The final will still be open from 8 a.m. to 11:59 p.m. over a 2-day period. The other exception is exam 3 that happens on a Wednesday. But if you have a conflict on that one and you don't have time to take it on the Wednesday, you can always just email me and we can figure it out closer to the test date. Another question, the 4% shaded for the z-score was 13.2 and some of the 13.59. Yes. So that's in reference to the empirical rule. Where did I draw? Here? Yeah. So we're between roughly -1 and -2 standard deviations, got a probability of 4.46. If we used the empirical rule over here, you're exactly right? 2.15% plus the 0.13 plus a portion of the 13.59 would give us the 4%. And I drew mine off. It should have been on this half because it's negative. Oops. Yeah. But more accurately, maybe I should use a different color. More accurately, minus 1.7 should be more along the lines of here and not close to -1. But I do a way better drawing of this in the pre-recorded video. So yeah, but you are right. You're drawing the right conclusions. So good for you.